Last night at 7:38 p.m. Eastern Time, sensors at NOAA's Space Weather Prediction Center registered something they hadn't seen in over 2 decades. A radiation surge so powerful that it triggered emergency protocols across 3 continents. Satellites went into safe mode. The International Space Station crew retreated to shielded compartments. And across the northern United States, from Alaska to Alabama, the sky began to glow with colors that shouldn't be visible this far south. What happened in the 24 hours between Sunday evening and Monday afternoon wasn't just another solar storm. It was the strongest solar radiation event since the Halloween storms of 2003, storms that knocked out power grids in Sweden and damaged transformers in South Africa. Welcome back. The sun just reminded us that despite all our technology, all our satellites, all our infrastructure, we're still at the mercy of a star 93 million miles away. And this time, we got lucky. At 1938 UTC on January 19th, Earth's magnetosphere absorbed the full impact of a coronal mass ejection, a billion-ton cloud of superheated plasma traveling at nearly 2 million miles per hour. The impact pushed geomagnetic conditions to G4 severe storm levels, the second highest category on NOAA's scale. But that wasn't the dangerous part. What concerned scientists most was the radiation storm that preceded it, an S4 severe solar radiation storm, the first to reach this intensity since October 2003. 23 years. That's how long it's been since we've seen radiation levels this high in Earth's vicinity. And here's what most people don't understand about these events. The pretty auroras we see in the sky, they're not the main story. They're just the visible symptom of something far more profound happening above our heads. Think about this for a moment. Right now, as you watch this video, there are over 9,000 active satellites orbiting Earth, communication systems, GPS networks, weather monitoring, military surveillance, financial transaction systems, your phone's navigation, your credit card payments. All of it depends on satellites that are currently being bombarded by radiation levels we haven't experienced in over 2 decades. During the Halloween storms of 2003, we had fewer than 1,000 satellites in orbit. Today, we have 9 times more infrastructure exposed to the same threat, and we've never tested how these modern systems handle this level of solar fury. That test is happening right now. The sequence of events began on January 18th at approximately 14 UTC when an active region on the sun's surface, cataloged as AR4341, unleashed an X-class solar flare. X-class flares are the most powerful category we have. They're the solar equivalent of a Category 5 hurricane, except instead of wind and rain, they release energy equivalent to billions of nuclear bombs. The flare itself traveled at the speed of light, reaching Earth in just 8 minutes. Radio operators worldwide reported blackouts, high-frequency communications disrupted, GPS accuracy degraded. But that was just the opening act. What came next traveled much slower, which gave us time to prepare, but also time to worry. The coronal mass ejection, that billion-ton plasma cloud, took nearly 30 hours to reach us. NOAA's Space Weather Prediction Center issued warnings, NASA contacted the International Space Station, airlines rerouted polar flights, and then, yesterday evening, it hit. Commander Reed Wiseman, one of the 4 astronauts preparing for next month's Artemis II moon mission, had just finished a press briefing about the historic launch when the radiation storm escalated to S4 levels. Suddenly, the conversation wasn't about returning to the moon, it was about protecting the astronauts already in space. The ISS crew, still recovering from last week's unprecedented medical evacuation, moved to the station's most heavily shielded modules. These are areas designed with extra protection specifically for events like this. But here's the uncomfortable truth. We don't know how much protection is enough during an S4 storm because we haven't had one in 23 years. The astronauts on the ISS during the 2003 Halloween storms reported seeing bright flashes behind their closed eyelids, cosmic rays penetrating through the station's walls and through their own skulls. Imagine that. Radiation so intense you can see it with your eyes closed. What does this mean for the Artemis II mission scheduled to launch in just over 2 weeks? NASA officials insist it won't affect the timeline. The wet dress rehearsal is still scheduled for February 2nd, launch windows still open on February 6th. But here's the question nobody's asking publicly. What if an S4 storm happens while 4 astronauts are in deep space, beyond the protective shield of Earth's magnetosphere, on their way around the moon? Apollo astronauts got lucky. Between 1968 and 1972, during the 6 moon landing missions, not a single major solar storm occurred during flight. It was statistical fortune. But Artemis II will spend 10 days in space, 10 days exposed, and the sun, as we've just been reminded, doesn't care about our launch schedules. Down here on Earth, the effects were more beautiful than dangerous. Aurora borealis, normally confined to latitudes above 60 degrees north, danced across skies as far south as northern Illinois, Wisconsin, and the Pacific Northwest. Social media filled with images of green and purple curtains shimmering over suburban neighborhoods. People who've lived their entire lives without seeing the northern lights suddenly had them visible from their backyards. In Montana and North Dakota, the displays were so bright they cast shadows. Photographers in Minnesota reported auroras strong enough to illuminate the landscape like twilight at midnight. This is what a G4 storm looks like when you're protected by Earth's magnetic field. It's breathtaking, but strip away that magnetic protection, put humans in deep space, and that same phenomenon becomes potentially lethal radiation exposure. NOAA's Space Weather Prediction Center has been tracking this particular active region, AR4341, since it rotated into view last week. Solar physicists knew it had the potential to produce major flares. They watched, they measured, they issued preliminary warnings. But even with our sophisticated monitoring systems, we can't predict the exact timing or intensity of these eruptions. We can see the conditions that might produce a flare the same way meteorologists can see conditions that might produce a tornado. But we can't tell you exactly when or how strong it will be until it happens. And once it does happen, we have between 8 minutes and 30 hours to prepare, depending on what's coming. That's the reality of space weather forecasting in 2026. We're better than we were in 2003, but we're still essentially watching a sleeping giant and hoping we notice when it starts to move. The last time we experienced an S4 radiation storm during those Halloween events of October 2003, the world looked very different. Facebook didn't exist. The first iPhone was still 4 years away. Tesla was a newborn company building its first roadster. SpaceX had never launched a rocket. Now, in 2026, we have a civilization that runs on satellites. Elon Musk's Starlink constellation alone has thousands of satellites providing internet to millions of users. A sufficiently powerful solar storm could damage or destroy significant portions of that constellation. And beyond communications, consider GPS. Modern agriculture relies on GPS for precision planting. Container ships navigate by GPS. Your phone's map function, GPS. Financial networks timestamp transactions using GPS. Military systems, obviously GPS. All of it vulnerable, all of it exposed. The 2003 storms damaged satellites and disrupted operations, but back then we had backup systems that didn't depend on space-based infrastructure. In 2026, we don't have those backups anymore. We've committed ourselves to a satellite-dependent civilization just as the sun enters one of its most active phases. Scientists at NOAA are already analyzing the data from this event. They want to understand why this particular coronal mass ejection was so powerful. What combination of magnetic field conditions, plasma density, and solar wind speed created an S4 level radiation storm? Because understanding this storm helps us predict the next one, and there will be a next one. The sun operates on an 11-year cycle of activity, moving from quiet periods called solar minimum to active periods called solar maximum. We're currently approaching solar maximum, expected sometime in late 2026 or early 2027, which means more sunspots, more flares, more coronal mass ejections, more opportunities for events like this week's storm, or potentially even stronger. Here's what I want you to think about. How many times has the sun produced storms like this when we weren't watching? Before we had satellites, before we had space weather monitoring, before we had NOAA's solar and heliospheric observatory stationed between Earth and the sun, constantly watching for these events. The sun has been producing flares and coronal mass ejections for 4.6 billion years. We've only been watching carefully for about 50 years. What did we miss? Write your thoughts in the comments. Do you think events like this are becoming more common, or are we just getting better at detecting them? The radiation levels are declining now. The immediate danger has passed. Satellites are coming out of safe mode. The ISS crew has returned to normal operations. The auroras are fading. By tonight, Earth's magnetosphere will have recovered, rebuilt its protective shield, and returned to normal. But the sun isn't finished. AR4341, the active region that produced this storm, is still there, still potentially active. And it's rotating into a position where any future eruptions would be pointed directly at Earth for at least another week. We're not out of the woods yet. Stay alert, keep watching the sky. And remember, that beautiful star that gives us life, warmth, and light can also remind us in an instant how fragile our technological civilization really is. Thank you for watching, and I'll see you in the next one.